right, so good job on the warm-up. I do want to show you one other way to think about simplifying radicals that you might already know, but if you have good number sense, some people like doing it this way better. So let's look at number 1 and number 2. Let's look at it in a different light. Some people, I'll just do this again. Some people don't use factor trees at all. Some people kind of consider factor trees like kind of like training wheels. But I'm not dissing it at all. You go ahead and factor tree like crazy. But some people have memorized all their perfect squares, and they use the number sense to think what perfect squares make up 20. So instead of picking 2 and 10, they don't pick that. Neither of those are perfect squares. They know to pick 4 and 5. And then all they do is just say, oh, square root of 4 is 2. And so they're already at their answer, and they didn't do any factor trees. They're square rooting perfect squares is what they're doing. So like on number 2, square root of 50. They're not going to pick 5 and 10 because neither of those are perfect squares. You're going to pick 25 and 2. Well, the square root of 25 is just 5. And so we're done solving it, and we didn't have to do a long, drawn-out factor tree. So if you do have good number sense, you've memorized those perfect squares, feel free to solve them this way. Don't feel like you're chained to the factor tree. Good. Good job. All right, let's check those homework answers. This is just 1 through 20 on one side of the paper. Go ahead and make sure you got all those right. I'll go to the next slide in a minute. Here's the second page of answers. These are the bottom to that front page right there. And then the back page of your homework is all on one answer slide. So there we go. Yeah, some of the radicals got a little bit off when we grouped them. Just, you understand. Oh, see, yeah, that 10 was a little bit wide. It's a grouping thing. All right, so today you can title your notes Multiplying and Dividing Radicals. So yesterday we learned to simplify, we learned to add, and we learned to subtract. We talked about how to add. You have to have like terms. You have to have the same radical to add and subtract them. Today we're going to see how we treat radicals when we need to multiply and divide them. Now, when I started yesterday, I first gave you an analogy, and I said 2x plus 3x, and you said it was 5x, and that was awesome. They were like terms. We combined them. But then I had something underneath that had x and y, and you're like, we can't do anything to that. That is already in its simplified form. We can't add them because they're not like terms. Now, we can treat radicals the same as variables even when we are talking multiplication. What is 2x times 3x? It's not 6x, right? We don't treat it like we're adding. We have to multiply the 2 times the 3 to get 6, and then we need to multiply the x times the x to get x squared. So we multiplied the integers together, and we wrote it down, and we multiplied the variables together, and we wrote it down. And that's exactly how radicals are going to work. What about down here, the next one? Yesterday we couldn't do a single thing with the one that had x's and y's. This one we actually can do something with it. We can write those two terms as one term. We can multiply the 4 times the 3. We're allowed to in multiplication, 12. And then technically we can multiply the x and the y, but we can't put them into one term. So something like that. So when you're multiplying, you're allowed to multiply radicals even when they are not like terms. So what do we do when we want to multiply a radical? Surprise, surprise. We multiply the numbers on the outside of the radical separate from the numbers inside the radical. So it's as easy as this. 3 times 4, 12. Square root 2 times square root 5, 2 times 5, square root 10. So you're allowed to multiply the radicands together. Go ahead and try these 3 examples, practicing your new skill of multiplying radicals. All right, let's go over these. So just like we said, you multiply the numbers on the outside separate from the numbers on the inside. Now, what's outside of that radical 3? It's just an understood 1. So it's just like saying 2 times 1. which is 2. So we multiplied all of our integers. Now we can multiply all of our radicals. Square root 3 times square root 5, square root 15, and yes, it is as easy as that. Next one. Multiply the numbers on the outside separate from the numbers on the inside. 4 times 6, 24, and square root of 10. Now, it always gets people when the radicand is an even number. They think that you can factor tree it and that there are perfect squares in it, but 10 is just 5 times 2. So 10 is totally simplified. That radical is. Number 3. Now, I talked briefly yesterday, and this is really important, about memorizing your perfect squares, but not just memorizing them, looking and finding them. Kind of like Where's Waldo? You have this huge paper and there's all these items and you're looking for one guy, Waldo. You don't want the fake Waldo, you want the real Waldo, right? So we are always on the lookout for perfect squares. Always on the lookout for perfect squares. Because if you can just square root that perfect square, it'll make your life so much easier. So on number 3, you play I Spy, and you're like, oh, I spy a perfect square. The square root of 4, it's just plain old 2. So you just get rid of it and you just write 2. That way you don't have to work with radicals when you don't have to. So this is really like saying square root 7 times negative 4, because negative 2 times 2 is negative 4. And so then you just write them together, always with the coefficient in front or the integer in front, and voila. So I did not do square root 7 times square root 4 and get square root 28 and have to factor tree the square root 28. You see what I'm saying? If you find and simplify perfect squares, many problems will go faster. All right. What about dividing radicals? Same process. Divide the numbers outside the radical separate from the numbers inside the radical. Nothing changes. So 6 divided by 3 is 2. Am I allowed to divide these? Yes, you're allowed to divide them. Students are sometimes scared because it's like there's 2 separate radicals and one's in the numerator and one's in the denominator. You're allowed to divide them. 8 divided by 2. And look at that. A blank blank. Perfect square, right? So the final answer is 2 times 2. Wow, who knew that 6 root 8 divided by 3 root 2 was just 4 all along? Okay, try these 3 problems, number 4, 5, and 6, and then we'll go over them. All right, so remember, we divide the numbers on the outside separate from the numbers on the inside. Negative 9 divided by 3 is just negative 3, and 42 is divisible by 7. That's really nice. It's square root 6. Once again, you kind of think, oh, that 6 is not reduced, but it really is. It is simplified because it has no perfect squares in it. Number 5. Literally, this is all you do on number 5. There's no radicals to deal with. Square root 5 can't be reduced. It doesn't have another radical to combine with or divide by. And so you reduce those and you get square root 5 over 4. It is not necessary to write the 1 because the 1 is understood. Okay, Megan got square root 5. So, Megan, did you spy the perfect square? Kind of had to in this problem, right? You wouldn't have really been able to do much because 5 is not divisible by 9. So you had to spy the perfect square. You had to find Waldo. The square root of 9 is actually plain old 3. It's not the square root of 3. It's not 3 squared. It's just 3. The 3's cancel, and you're left with final answer, square root 5. Okay, here's the good part of the lesson. This is a very important part of the lesson. I want you to write down all 3 things on this checklist. Title it, Checklist for Simplifying Radicals. So let's take a look at this checklist. Obviously, the radicand can have no perfect squares left. You know you're not done if it still has perfect squares in it. For example, the square root of 8, that would not be done yet. Okay, so anyways, what I was saying is that there's a perfect square left in 8, so that would not meet our checklist. Second of all, the radicand is not allowed to have fractions. So this would be disobeying the second one on the checklist if there are fractions inside the radical. Now, if there's a fraction as an answer, that's fine. Just can't be inside the radical. Finally, you are not allowed to have radicals in the denominator. So that last one would disobey the third thing on the checklist. And if you have radicals in the denominator, it means your denominator is irrational. What's the opposite of irrational? Rational. So the next few slides, we're really going to focus on this one right here. If there's a radical in the denominator, if your denominator is irrational, we're going to work on forcing it to be rational. So we're going to do something called rationalizing the denominator. Write it down. Oh, I'll come back to this. Write down rationalizing the denominator. Rationalizing the denominator. When the denominator is irrational, we're going to force it to be rational. Okay, I'll come right back. We need to have this one skill to be able to rationalize the denominator, which is something you'll use in future maths a lot. So, square root 3 times square root 3 is 3. Square root 27 times square root 27 is 27. Square root 1,289 times square root 1,289 is 1,289. It's important that we can write that right away. You don't need to write square root of 3 times square root of 3 is square root of 9 and then take the square root of 9. You don't need to do the middle step. The square roots simply cancel and you get 3. It's like saying square root of 3 squared. You know, the square and the square root cancel, and that's why you're left with just 3. Okay? All right. So, when your number has a radical in the denominator, it is wrong. You have not simplified it. So we're going to learn how to rationalize the denominator. The way you rationalize it is you multiply that number by 1. You multiply it by 1. That's how you do it. But it's not any old one. It's a very fancy number 1. It's a very fancy number 1. It's a very intentional number 1. So you're going to multiply that by square root 3 over square root 3. Do you agree that that's just 1? So I'm not changing it, I'm just rearranging. Okay? Why did I pick square root 3 over square root 3? Where did that come from? I just looked at my denominator. All right, let's multiply this out. 1 times square root 3. It's just square root 3. So I'm multiplying across the top. Now let's multiply across the bottom. Square root 3 times square root 3. And I totally get it. I totally know that the original one looks more simple than the answer, but that is the simplified answer. It meets every box on the checklist. All right, try these problems. I'll give you a few minutes to work on them. Make sure that your final answer meets every box on the checklist. All right, let's start working these. Number 7. I spy a blank blank. What did you see on number 7? A perfect square. Don't keep this as square root of 4 for long. Write what it really is, which is 2. So now we have 2 over square root 5. I'm obeying box number 1. I'm obeying box number 2. I'm not obeying box number 3. We broke the rules. There's a radical in the denominator. So now we need to multiply by a really fancy number 1. How did I pick which number 1 to multiply by? I looked at the denominator. All right? So I'm going to multiply across the top. 2 times square root 5 is 2 root 5. Square root 5 times square root 5 is 5. Final answer, 2 root 5 over 5. Number 8. I'm obeying rule number 1. I'm obeying rule number 2. It's that rule number 3 that we're breaking again. So we are going to multiply the numerator and the denominator by the radical in the denominator. 1 times square root 2 is just root 2. Square root 2 times square root 2 is 2. So square root 2 over 2. This one looks just like the one that we did in the example with the 3, right? Number 9. Oh man, I don't spy any perfect squares. All right, let's just go ahead and start to rationalize. So multiply the numerator and the denominator by square root 8. Square root 5 times square root 8 would be square root 40. Square root 8 times square root 8 is 8. Now I'm not done because I'm disobeying the first step of my checklist, which is not allowed to have perfect squares in the radicand. So we factor tree it, or you use your number sense and you realize, oh, that's 2 root 10. Oh, we're still not done. Here, I'll draw another arrow. We're still not done because 2 over 8, that can be reduced. 2 over 8 is 1/4. So the final beautiful answer is square root 10 over 4. Woo! 10, 11, and 12. Go ahead and try those. All right, here we go. Number 10. We are disobeying checklist number 2. Bullet point number 2 in our checklist. We haven't really disobeyed that one before. So let's go ahead and separate these. And now we've got that radical in the denominator. So now we're going to rationalize it. That means force the denominator to be rational. It is irrational and we are making it rational. Okay, we're going to multiply across the top. Square root 2 times square root 3 is square root 6. Multiply across the bottom. Square root 3 times square root 3 is just 3. The more you do of these, the quicker you're going to get. Number 11. Now, we've never had an integer in the denominator with our radical. Do not bring that along when you write your fancy number 1. Ignore the integer. So when I rationalize, I'm just going to multiply by root 6. I'm not multiplying by 2 root 6 because that's redundant and unnecessary. All right, let's make sure we can all do this correctly. Let's multiply across the top. That's the easy one. 3 times root 6. Just 3 root 6. You just write them next to each other. Now across the bottom, 2 times 1, because there's a 1 sitting in front of that root 6. Just 2. Square root 6 times square root 6, that's no different. It's just 6. So that was a little bit different than the other ones. So the numerator is still 3 root 6. The denominator is 12. Boom, boom, 1/4. We love to have denominators of 4 in our final answer, don't we? I don't know. Did you get it right? Last one. I spy perfect squares. I spy 2 of them, in fact. I would rewrite this if I were you, because we are allowed to do that. That is mathematically legal. You can square root the top and square root the bottom. Totally legal. Alrighty. The numerator is completely a perfect square. The square root of 49 is 7. The square root of a to the 6th is a to the 3rd, because you just divide the exponent by 2, if you remember that from yesterday. But we still have a problem because we're disobeying that last rule. There is a radical in the denominator, and it's not simplified when there's one there. So we're going to rationalize. Dun, 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 dun. So the numerator is 7a cubed root 6. And the denominator is 6. 7a cubed root 6 over 6. Yay!